A plus B goes to C in a CSTR. Inlet temperature 27 Celsius. The feed is stoichiometric. The entering volumetric flow rate is 2 liters per second. The rate equation is given, and the initial concentration of A is also given. More stuff. At a reference temperature of 0 Celsius, the enthalpy of A is equal to minus 20. The enthalpy of B is equal to minus 15. The enthalpy of C is equal to minus 41. All of these are in kilocalories per mole. The heat capacity of A is the same as the heat capacity of B. It's 15. Heat capacity of C, 30. And these are in calories per mole Kelvin. A little bit more info. The rate constant is 10 to the negative 2 liters per mole seconds. Also at, well no, at a different temperature, at 300 Kelvin. And the activation energy is 10 kcals per mole. Okay, everybody got that down? That's horrible. Just the amount of information that you need.
And all the units.
Yeah. Units are pretty consistent though. At least there's no like BTUs mixed with different kilojoules. They're all calories and moles.
BTU pound mass per Rankine.
Yeah, it could be worse, right? All right, what we want to do is, we'll do it over here. All right, we want to find the volume of the CSTR for that conversion and an adiabatic reactor. So where do we start? Design equation. That's often a good place to start, so let's do that. So for a CSTR, it's just the volume is equal to the initial flow rate of A times the conversion divided by the rate of the reaction.
Stoichiometry of the rate of the reaction.
Rate equation comes next. And this one's just given. And now stoichiometry. So the concentration of A, which again, we need that because that's how our rate equations are written. Concentration is the flow rate of A divided by the volumetric flow rate. Does that change for this system? Why not?
Liquid.
Liquid phase system, so I can go ahead and just put the inlet volumetric flow rate, which is conveniently given to us.
What if you did have like mass? What if you did have a gas
you had phase change? In a CSTR, yeah, I mean, you'd have to, suddenly V would not be constant anymore. You'd have to account for that. Okay, and remember that I can write that in terms of the speed of A, which is what we always do. And what is this? The initial concentration of A, which is given. And what is CB? Is anything different? No, right? CB is also equal to CA naught times 1 minus X. And this is because theta B is equal to 1. And they have the same stoichiometric coefficients. All right, so if we combine these things as if we haven't worried up until now, right? We ignore the whole temperature is not what we think it is. Then we just get the volume is equal to the flow rate of A times the conversion divided by rate constant, CA naught squared, 1 minus conversion squared. And what do we know about the rate constant? What equation do we have for it? The Arrhenius equation. So the rate constant is equal to A times the exponent, the activation energy divided by RT. So any questions? All right, what do we do next? Energy balance.
Is that needed? If we already have X.
Yeah, because the temperature changes.
Do you know what the temperature of the reaction is?
Oh,
Wasn't that very last equation though that we wrote, that the temperature in terms of X?
Yeah, I mean, the energy balance. We're going to write that equation, yes. So why do we need it, though? We don't know the rate constant, because to know the rate constant, we have to know the temperature, and we don't know the temperature. For that, we need the energy balance. Of course, everything else in here we know. We're just missing that rate constant, and we can't assume that it's 300 Kelvin just because that's the rate constant we were given. All right, so from the energy balance that we've already had on the board, we have an adiabatic system, and so we can jump straight to temperature as a function of conversion. Why do we use that one? Because we know the conversion, we don't know the temperature, right? So the equation that we had up on the board, I'll write it back up here. And you'll notice that I'm going ahead and I'm substituting in those summations. Just remember that theta A is equal to theta B is equal to 1 because the stoichiometric field. So any questions about where that seemingly random equation has come from? Yeah. Conversion times the delta H of reaction at a reference temperature and at standard conditions. So this is not the heat of the reaction at whatever temperature you're operating at. This is at a reference. Okay. So were we given the delta H of reaction at a reference temperature? Now what were we given? What was the reference temperature?
273.
Or no, sorry, we weren't given this. We were just given enthalpies. So that's going to be equal to the enthalpy of C minus the enthalpy of B minus the enthalpy of A. Any questions about where that equation came from?
You put the coefficients, right? But it's just 1.
Exactly. The coefficients do matter here, but this is just A plus B goes to C, so they're all 1. All right, and so you get minus 41 minus a negative 20 minus a negative 15. And that's the final answer, minus 6 kcals per mole. So if you weren't given those enthalpies, but instead I gave you a reaction, in other words, I actually gave you the chemical species, not A plus B goes to C, what would you do in order to get the delta H of reaction at standard condition? What am I looking up in those lookup tables? Enthalpies? Right. Delta H is a formation, not just enthalpies, but delta H of formation. And so we did an example like that for ammonia synthesis. And in those cases, the reference temperature won't be 0 Celsius, but more commonly 298. Okay, what else do we need? So that's that conversion we're given.